It just because the other option to have either me and JP. So like he had a problem with it.
Okay. Do I have all of the KSP labs? Just as a reminder, things that you have due. You do have a homework and a quiz due on Monday. On Wednesday, you have the thermodynamics lab due. And on Friday of next week, you will have the final versions of your service learning project, as well as the electrochemistry lab that we're going to be doing next week due. The Monday after Thanksgiving break will be exam 4, and that is also the day that your self-reflection for your service learning project and your group reflection for the service learning project is due. So that kind of gives you an idea of what's to come. There is also a homework and a quiz that will be due the Monday of Thanksgiving week. So that will be over next week's information. Any questions? If not, then we're going to go ahead and get started into today's information. So on Wednesday, we started our discussion on whether a reaction will occur or not, and Gibbs free energy determines whether a reaction will occur or not. We can calculate Gibbs free energy. Using a few different methods. The ones that we're going to talk about today is we're going to talk about delta G naught is equal to delta H naught minus T delta S naught. We're also going to talk about delta G naught is equal to negative RT natural log of K. Now, with respect to Gibbs free energy, If it turns out to be a negative delta G, that means that the reaction is spontaneous. When we say something is spontaneous, that means that the reaction will occur without additional external influences. If it comes out to be a positive delta G, that means that the reaction is non-spontaneous. And basically what that means is that you will have to either continuously add energy, add pressure, add something. In other words, you will have to continually alter the environment of the system in order for the reaction to occur. Now, to calculate delta G naught using delta H naught minus T delta S naught, there are a few things that you need to pay attention to. Number one, delta H, when we calculate it, will be in kilojoules. T must be in Kelvin. And S naught, you will need to change to kilojoules. From joules. In order to be able to finish this calculation. In other words, the units must match. For delta G naught is equal to negative RT natural log of K. The delta G naught will need to be in joules. That is because the R we will use is 8.314 joules per mole Kelvin. That forces our temperature to be in Kelvin. So again, with these calculations, the equations are not hard. What students tend to miss on these equations is not paying attention to their units. So pay attention to your units. Now, before I begin the calculation, there is one more thing I want to mention, and that is if a reaction, is at equilibrium, then delta G naught is equal to 0. Now, what this allows us to do is it will allow us to determine the temperature in which interconversion between spontaneous and non-spontaneous will occur. In other words, it will allow us, that fact will allow us to determine the temperature where a non-spontaneous reaction would become spontaneous, and where a spontaneous reaction would become non-spontaneous. The way this works is if you take your delta G naught is equal to delta H naught minus T delta S naught. And if delta G naught is equal to 0, that is equal to delta H naught minus T delta S naught. Rearranging this equation and solving for the temperature, you will get that delta H naught divided by delta S naught will equal this temperature that we're talking about, where the spontaneous will change to non-spontaneous, or where non-spontaneous will change to spontaneous. So just to recap, we are going to perform Gibbs free energy calculations today. We are going to use two different equations to accomplish that task. The major issue with these equations, because they're fairly straightforward, is making sure that the units match. And then the other thing we can do is figure out where at what temperature a non-spontaneous reaction will become spontaneous, using the fact that a reaction at equilibrium has a Gibbs free energy of 0. That means it's perfectly at equilibrium. So let's look at some examples. We're going to look at the reaction where methane gas reacts with 2 oxygen gas to form carbon dioxide gas plus 2 water gas. The delta H of formation for these compounds in kilojoules per mole are -75 for the methane, 0 for the oxygen because it's in its standard state, a -393.5 for carbon dioxide, and water in the gas form is a -242, according to the table I have in front of me. The S naught, which is in joules per mole Kelvin, is equal to 186 for methane, 205 for oxygen, 214 for carbon dioxide, and 189 for water in gas form. You will receive on the optional homework, you will have to look at the table in the back of the textbook or pull up a thermodynamics table to get the data. Now, if you look at the answer key, except for I think on the first problem, I actually wrote it out at the very, very top. So if you can just check out the top and then do the rest of the math yourself. On a test, you will receive a table to work from. Now, if we're going to calculate delta G, we've got to calculate delta H naught for the reaction and delta S naught for the reaction. Again, delta H naught of the reaction is equal to the sum over the products of the number of moles times the delta H of formation minus the sum over the reactants of the number of moles times the delta H of formation for those reactants. So our delta H of reaction is going to equal, we have 1 mole of carbon dioxide times -393.5 kilojoules per mole, plus we have 2 moles of water times a negative 242 kilojoules per mole minus the reactants. In the reactants, we have 1 mole of methane times a negative 75 kilojoules per mole. And we have 2 moles of oxygen times 0 kilojoules per mole. When you key this into the calculator, you get a delta H naught of a delta H of a negative 802.5 kilojoules. So what we know about this is that it is exothermic. Heat is a product. And it is spontaneous with respect to enthalpy. We now need to calculate delta S naught. Delta S naught is equal to the sum over the products of the number of moles times the S naught minus the sum over the reactants of the number of moles times S naught. So our delta S naught is going to equal 1 mole of CO2 times 214 joules per mole Kelvin plus 2 moles of water times 189 joules per mole Kelvin minus 1 mole of methane times 186 joules per mole Kelvin plus 2 moles of oxygen times 205 joules per mole Kelvin. So our delta S naught comes out to be equal to a value of -4 joules per Kelvin. So with respect to delta S, this is non-spontaneous with respect to entropy. Now that you have your S and your H, your enthalpy and your entropy, you can calculate delta G. Delta G naught is going to equal delta H naught minus T delta S naught. So our delta G naught is going to equal -802.5 kilojoules minus T. Now, folks, if you are not given a temperature, assume it is under regular conditions, which is 25 degrees Celsius or 298 K times delta S naught, which we calculated as negative 0.004 kilojoules per Kelvin. So you will notice two things. Number one, well, three things. Number one, because I was not given a temperature, I assumed it to be 25 degrees Celsius. Number two, I changed that temperature to Kelvin, so it's 298 Kelvin. And number three, I changed the entropy to kilojoules to match the enthalpy. When you key this into the calculator, you get a value of a negative 801.3 kilojoules. Because it is negative, this reaction is spontaneous. Questions? Let's look at another example. P4H10 solid reacts with 6 water liquid to form 4H3PO4 solid. Looking up the enthalpies of formation, which is in kilojoules per mole, P4H10 is a negative 2984 kilojoules per mole. Water liquid is a negative 286 kilojoules per mole. And H3PO4 solid is a negative 1,279 kilojoules per mole. The S naught in joules per mole Kelvin for P4O10 is 229. P4O. That was, excuse me, that is supposed to be O10. Is 229. For H2O liquid, it is 70. And for H3PO4, it is 110. Again, those numbers are coming from a table, and you'll be given the table on the test. On the homework, you can look up those numbers on my answer key for all but the first problem. Otherwise, you got to go to a textbook or a table of thermodynamics. Okay, so let's get into the delta H naught. That is going to be the products. So we have 4 moles of H3PO4 times that value of 1,279 kilojoules per mole minus the reactants. We have 1 mole of P4O10 times negative 2984 kilojoules per mole. Plus, we have 6 waters times negative 286 kilojoules per mole. So keying that into the calculator, you get a value of negative 416 kilojoules. So this is exothermic. Heat is a product. And it is spontaneous with respect to enthalpy. Now let's calculate delta S naught. Delta S naught is 4 moles of H3PO4 times 229 joules per mole Kelvin minus the reactants. It is, I'm sorry, it should be 110. Minus the reactants, which is 1 mole of P4O10 times 229 joules per mole Kelvin, plus 6 waters times 70 joules per mole Kelvin. So 4 times 110 minus 229 minus. When you key this into the calculator, you get a delta S naught equal to 631 joules. Let me double check that. Excuse me, that is incorrect. It didn't feel right. That's a negative 209 joules per Kelvin. So again, this is non-spontaneous. With respect to entropy. Anybody want to tell me why I knew I made a mistake? There's a multitude of reasons, but the big reason is I came up with a positive number. And I knew it couldn't be positive because I went from a liquid and 7 molecules to just 4 and a solid.
Out of all 3 of these equations we come out, why are 2 of them spontaneous and 1 of them is non-spontaneous?
Okay. So, the fact of the matter is, you can have 4 options, really. You can have an enthalpy that's spontaneous and an entropy that's spontaneous, which guarantees that the reaction's spontaneous. You can have an enthalpy that is non-spontaneous. You can have an entropy that is non-spontaneous, and the reaction will be non-spontaneous. But you can have an enthalpy that's spontaneous and an entropy that's non-spontaneous, or vice versa. And what it means is one of those is going to control the reaction. So I could have let's just do it this way. So we can have a negative, a positive, and this one will be negative and spontaneous. No option. We can have a positive, we can have a negative, and this one will come out positive and be non-spontaneous, no option. But we can also have a negative, or a positive and a positive, and then you have the option. It may be spontaneous, or non-spontaneous, depending upon the environment, specifically temperature. So what I guess I'm trying to say is, I just happened to pick two problems that did that. That was negative and negative. But I could have gotten other options here. And anyhow, in these last two, it's all going to depend upon the environment, whether it's spontaneous or non-spontaneous. Temperature is the biggest controlling factor. But depending, I mean, if you have a lot of gases, you can also get pressure behind it. So there's other things that could control it. It's just temperature is the biggest controlling factor. Does that answer your question?
Is delta H and delta G, like if you have differing delta H and delta S, is it always going to be directly correlated to delta H?
Not necessarily. Most of the time, yes. If you have opposite arguments being posed by enthalpy and entropy, the enthalpy does tend to win out, but not always. Okay, so our delta G is going to equal negative 416 kilojoules minus T, 298 Kelvin, times negative 0.209 joules per mole Kelvin. I mean, excuse me, joules per Kelvin. So our delta G naught here comes out to be a negative 353.718 kilojoules. Yes.
So with all that being said, you said temperature is like a really big factor if they're both negative or both positive. Is temperature always 298 unless told otherwise? Unless
I tell you otherwise, assume 298. Because And the reason for that is delta H is a formation, and the S not that you find in textbooks are all recorded at 25 degrees Celsius. So most of our data is at 25 degrees Celsius unless you're told otherwise.
So if it's 298 most of the time, will delta H equal to delta U? Will they be?
Not necessarily. You've got to do the calculation to know. So with this particular question, since a lot of these questions are coming up, what temperature will cause this spontaneous reaction? To become non-spontaneous? That's where basically for it to go from spontaneous to non-spontaneous, that's where delta G is equal to 0. That's your equilibrium. So at equilibrium, delta H naught minus T delta S naught is equal to 0. So if we rearrange this equation, we can find out the temperature at which things will undergo a change by taking the delta H and dividing it by the delta S. So we had a negative 416 kilojoules. If we divide that by negative 0.209 kilojoules per Kelvin, we will find out the temperature at which this is going to become non-spontaneous. And basically, this reaction becomes non-spontaneous at 1990 Kelvin. So what this tells me is at lower temperatures, this reaction is likely to be spontaneous. I mean, for me, it makes sense because at higher temperatures, the water is going to boil off. You're going to have other things going on. Let's look at one more example. And I want you to calculate the enthalpy, entropy, and free energy for hydrochloric acid gas reacting with ammonia gas to form ammonium chloride solid. The delta H of formation in kilojoules per mole for HCl is -92. For ammonia, it's -46. And for ammonium chloride, it's negative 314. The S naught for this set of chemicals is 187 for the hydrochloric acid, 193 for the ammonia, and 96 for the ammonium chloride. Okay, let's see how it's going. So you should have calculated the enthalpy to be a negative 176 kilojoules, which means it's an exothermic reaction. It means that the heat is a product of the reaction, and it means that the reaction is spontaneous with respect to enthalpy. You should have calculated the entropy to be a negative 284 joules per Kelvin, which means that with respect to entropy, it is non-spontaneous, which we could have predicted because we made a solid from two gases. And then when you calculate Gibbs free energy, making sure that your units match, you should have got a negative 91.368 kilojoules, which means it's spontaneous. Now, there is one other thing that we have described that tells us whether a reaction is going to go in the direction that it is written. And what is that other thing? The equilibrium constant. If you have a really large equilibrium constant, you expect the reaction to go to completion. If you have a really tiny equilibrium constant, you expect the reaction to not go anywhere. There is a correlation, therefore, between Gibbs free energy and the equilibrium constant, and that correlation is that delta G naught is equal to a negative RT natural log of K. This is the correlation between Gibbs free energy and the equilibrium constant. Now, again, you have to pay attention to your units. So your delta G naught is going to need to be in joules for this calculation. So it's negative 91,368 joules. That is because the R that you're going to use is in joules at 8.314 joules per mole Kelvin. It means your temperature needs to be in Kelvin, and that will allow you to calculate your equilibrium constant. So using our information for the formation of ammonia from hydrochloric acid and ammonium chloride from the reaction of hydrochloric acid with ammonia, we would have a negative 91,368 joules is equal to a negative 8.314 joules per mole Kelvin times the temperature in Kelvin of 298 Kelvin times the natural log of K. The natural log of K, when you complete the first portion of this calculation, comes out to be equal to 36.878. Taking the exponential of both sides, that will get rid of the natural log. And so when we actually key that into the calculator, we get 1.037 times 10 to the 16th is equal to our equilibrium constant. This makes sense. It makes sense because you have a fairly large exponent for the equilibrium constant, telling me that this reaction should go to completion. It should go towards the product and go significantly towards those products. Just like my negative in the Gibbs free energy tells me that this reaction should go towards the product and should go significantly towards the product. We are going to do a little bit more with equilibrium constant, but on Monday, I'll do one more problem, but on Monday, we are going to talk about Gibbs free energy under non-standard conditions and how you calculate it. And we'll also start getting into balancing redox reactions, which gets us started into electrochemistry. If you need a review on redox, I did post a video that is a review of redox from College Chemistry 1. So that you can review a little bit before we get into it. I will see you all on Monday.
Did we need to worry about like a video?
No, you're not gonna have to worry about that.
Okay. Sorry.
I turn this in today, right?
Yes.
Okay, cool. Do you happen to have any of the bear pantry phone drops or shot of to that bird?
The what?
The bear pantry.
I don't have it because you gotta fill it out.
Okay,
I
well,
don't print them off.
okay. I'll do that. Are you gonna be going straight to your office?
I have another class.
So I just did it before too, so where should I drop it off?
Drop it off in the office in 205, but I have a class until 1.
Okay. Thank you.
Could I ask you a question? Did you add me to your class for Maximaster even though it's a wait list?
I have no control over stuff like that. The only people that do are in Manion 205.
Thank you.
So, yeah, I can't add anybody. They'll do it only for